Last episode, we taught a single attention head some manners, the causal mask, no peeking at the future, every token allowed to look left but never right. And it worked. That one head learned to pass information backward through time. But here's the thing about one head, it can only learn one relationship at a time. Language doesn't work like that. A single sentence carries grammar and subject and tense and tone, all of it all at once. So, in this episode, we stop asking one head to do everything. We run several heads in parallel. This is multi-head attention. Think back to that single head. It found one pattern, maybe which verb belongs to which noun. Useful. But a sentence is layered. One relationship is never enough because the meaning lives in many relationships overlapping. So instead of training one head harder, we train many heads side by side, each free to specialize. Here's the picture I want you to hold. Imagine 4 people reading the same sentence. One only cares about grammar, who's doing what to whom. One tracks the subject across the whole line. One watches the tense, one listens for the tone. 4 readers, one sentence, 4 colored lenses. And when they compare notes, you understand the sentence far better than any single reader could alone. So how do we make 4 readers out of one vector? We split the channels. Each token carries a 32 wide vector. We cut that into 4 strips of 8. Head 1 gets the first strip, head 2 the next, and so on. Each head attends inside its own slice. Same total width, just divided into independent viewpoints. And the beautiful part, this is basically free. 4 heads of size 8 cost the same as 1 head of size 32. It's the same total arithmetic, just reshaped. You're not paying more compute. You're buying more viewpoints with the budget you already had. Each head finishes with its own little output, a stack of 8 numbers per token. Now we stitch them back together. Concatenate. Lay the 4 heads outputs side by side along the channel dimension, and you're back to one wide vector of 32. 4 small answers glued into one. But concatenating just parks them next to each other. They haven't actually talked yet. So we add one more step, a final linear projection. It takes that stitched together vector and mixes it, letting what grammar head learned inform what tone head learned. The projection is the conversation between the heads. One PyTorch detail that trips people up. We hold the heads in an nn.Module list, not a plain Python list. Why does it matter? Because nn.Module walks module list when it collects parameters. Put your heads in a regular list, and a PyTorch never sees their weights. The optimizer never trains them, and you'll spend an afternoon wondering why your loss won't move. Module list is how PyTorch knows these submodules are yours. So that's multi-head attention, split, attend in parallel, concatenate, project. 4 lenses on one sentence blended into one richer view. Let's go build it. B0, overview. Here's multihead.py, it's short. We import torch, we reuse the causal head from last episode. We wrap a list of heads in a multi-head attention module, and we run one batch to watch the shapes flow through. 2 pages, the imports, hyperparameters, and the whole head class on page 1. The multi-head attention module plus the run and print on page 2. Let's walk it. Top of the file, the usual imports, then our hyperparameters. Batch of 4, block size 8, so 8 tokens per sequence. Embedding width 32, 4 heads, which makes each head size 8. Notice head size is just n EMBD divided by n head, 32 over 4. That division is the whole split the channels idea written as one line. Next, the causal head, exactly what we built last episode, brought along so the file runs on its own. Key query value projections, the scale dot product, the lower triangular mask filled with negative infinity, so the softmax can't look forward, then weighted sum the values. Each head takes the full 32 wide input and returns its own 8 wide output. We are not rederiving it, just reusing it. That's the end of page 1. Page 2 opens on the star, multi-head attention. In init, we build an nn.Module list with a list comprehension and head copies of head, each of size head size. That module list is the line that makes the optimizer see every head. Then one anode linear from head size xn head to any MBD, 8 times 4 into 32. That's the blending projection at the end. The forward is 3 lines and they're the whole episode. First, run every head on the input and concatenate their outputs along dim.1, the channel dimension. 4 8 wide outputs become one 32 wide tensor. Second, push that through the projection. Third, return it. Split, attend, concat, project, right there. Still page 2, the runner. We make a random input, batch for 8 tokens, 32 channels, standing in for a batch of embedded sentences. We build the module, then we peek at one single head on its own so we can print its shape. We grab the concatenated tensor and we run the full module. And we print number of heads and head size, the per head output shape 4 by 8 by 8 one head's view, the concatenated shape 4 by 8 by 32 all heads stitched, the shape after projection still 4 by 8 by 32 same size but now blended, and one last human line, 4 heads, 4 views of the same sentence, closer, teaser. So attention now mixes information across tokens. Every token gathers context from its neighbors through 4 lenses at once. But mixing isn't thinking. After a token has collected everything it can see, it still needs a moment to process that on its own, to take the gathered context and transform it. That's the other half of a transformer. Next episode, we bolt attention together with a little neural network and the residual connections that hold it all up, the transformer block.